Today we'll be looking at operations with algebraic vectors in R2. So to begin, let's define a vector in R2. So a second way of writing the vector OP is equal to AB is the use of the unit vectors I and j. So the vectors I, which is equal to 1, 0, and j, which is equal to 0, 1, have a magnitude of 1 and lie along the positive x and y axes respectively, as shown on the graph. So let's just show this to you on the graph. So this is our I, okay, from our origin, okay, O, and this is our I, and this here is our j. Okay, notice with your I here, the point that exists is 1, 0, and the point here with your j, that point that exists is 0, 1. So what we want to do here in our first example is we want to write each in term of its unit vector form. So we first have our vector OP, which is equal to negative 4, 5. So to write that, okay, in term of its unit vector, all we need to do, since our first value it is respected to I, so we have negative 4i, and then our 5, okay, relates to our j, so plus 5j. So our I and j, remember, are unit vectors. And then we want to write the vector OQ with the point Q equals negative 3, 0, as well in unit form. So we will have OQ is equal to just negative 3i, since our y value here is 0, so we don't have any j for our unit vector. So when talking about representations of vectors in R2, the position vector OP can be represented as either OP is equal to AB or OP is equal to A times our unit vector I plus B times the unit vector J, where O is just our origin, that 0, 0, and P at AB is any point on the plane, and I and J are in standard unit vectors in R2. So recall here, when it's R2, we're just discussing our x and y planes. Our standard unit vectors, I and j, are unit vectors that lie along the x and y axes respectively. So I, which is equal to 1, 0, and j, which is equal to 0, 1. Every vector in R2, given in terms of its components, can also be written uniquely in terms of I and j, are also called the standard basis vectors in R2. So we're going to go and look at our example here. We are given that x, or vector x, is equal to 2i minus 3j, and that y is equal to negative 3j, and we want to determine the magnitude of x. So just to give us a visual of what this might look like, since we have 2i, we know our unit vector is a magnitude of 1. So on my graph here, I'm going to draw my 2, okay, so this here is my 2i. Okay, the magnitude of 2i is just equal to 2. Since I know the magnitude of I is 1, we multiply that by 2, so we get 2. And when we're talking about negative 3j, because that comes from our x vector here, so that was our negative 2i, and then here, this would be our negative 3j, which would be equal to 3, so the magnitude there. So this here is our x. So how can we find x? Well, normally to find x, you're going to take your 2 points and you're going to minus them from one another, but since our points when it lies on our unit vectors are I and j, so that point there would be 2, 0, and the point here would be 0, negative 3. We're just going to use those values respectively. So what I mean by that, we can therefore have x, when we're finding the magnitude, I don't need to do my whole x2 minus x1 and then adding my y2 minus y1 and taking the square root of that, because I have zeros for one of my x's and I have zeros for one of my y's. So I can just write 2 squared plus 3 squared, which is going to equal the square root of 13. Now, if we look at y here is just negative 3j. So, giving ourselves a visual here, when we look at this, we don't have any i's, so therefore we know I in all cases is just 0. But for our negative 3j, okay, this would be negative 3j. I know my magnitude is equal to 3 there. So when I have my y, and we're taking our magnitude of our vector y, we just have the square root of 3 squared, which will just be equal to 3. Now we'll continue by looking at the addition of two vectors using component form. So we want to determine the sum of OA, which is equal to our A plus B, AB, and our OD, which is equal to CED, and where A and B are any 2 points in R2, as you can see here in our visual diagram. So let's start by writing OA and OD in our component form. So OA is going to be equal to AI plus BJ, and OD will be equal to CI plus DJ. So now we want to determine the sum. What does sum mean? So remember, sum just means addition. So we add OA plus OD. And when we add those, we're going to add our AI plus BJ plus our CI plus DJ. So we can strictly go ahead and add our like terms, so our AI and our CI. So we have AI plus CI, and then we have BJ plus DJ. Now, what is common in our first two terms here? The unit vector I. So let's factor that out, and we're left with A plus C. Similarly, in our second two terms, we're going to factor out that J, and we're left with B plus D. So therefore, we can say that OC is equal to A plus C and B plus D. Okay, in our visual here, this would be our C, which is A plus C and B plus D. So therefore, OA plus OD is equal to AB plus CD, which is equal to A plus C and B plus D. And similarly, OA minus OD would just be AB minus CD, which is equal to A minus C and B minus D. So now let's look at our scalar multiplication of vectors using components. So given OP, the vector OP is equal to AB, we want to determine the coordinates of MOP, where M is a real number. So what we'll have here is M times our vector OP, which is equal to M times AB. So we can change our AB to component form, so AI plus BJ. And then we're going to multiply that M into both terms. So what we notice here is that we have MA and MB. So, and then they're multiplied by our components. So therefore, M times our vector OP is just equal to MA plus MB. So now, in example 3, given that A, which is our vector A, which is equal to the vector OA, which is equal to 1, 3, and B is equal to the vector OB, which is equal to 4, negative 2, we want to determine the components of A plus B and A minus B, and illustrate each of these vectors on the graph. So let's go ahead and just do our A plus B first. So A plus B was equal to our OA plus our OB, which is just equal to our 1, 3 plus 4, negative 2. And then we know that we can just add these values together. So from looking at our addition above. So what we do is we add 1 plus 4, which gives us 5, and 3 plus negative 2, which gives us 1. Now let's look at our A minus B vectors, which would just be OA vector minus the OB vector. So which is 1, 3 minus 4, negative 2. So 1 minus 4, we get negative 3, and 3 minus negative 2, we have 5. So now let's do the second part of this example and illustrate our vectors. So I'm just going to draw our axes here. So our x and our y-axes. So let's first label our vectors A and our vectors B. So we know that it's at 1, 3. So remember, always start at the origin, over 1 up 3. Okay, so this would be A. And it goes from our origin, because it's OA. And then our vector B, which is OB, okay, is going to be at 4, negative 2, and then from the origin. So our B value is right here. So that's our B. And then what we need to do is we need to look at our A plus B. So we know that's going to be at 5, 1. So this vector right here is our A plus B. And we also, which if you can see here, if I were to translate that vector B up, okay, this would be also our vector B. Oops. And then we can also graph our A minus B, which is negative 3, 5. Okay, so that's our A minus B, which I could therefore graph our negative b, because negative b is just the opposite here. So that would be our negative b. So there's our illustration, our a plus b, and our a minus b. So now moving along, looking at vectors in R2 defined by 2 points. So given the points A, which is located at 1, 4, and B, which is located at 4, negative 1, we want to determine AB and also the magnitude of AB. So first let's graph A and B. So A here, alright, hard to see that axes there. Sorry, that should have been in red or black. Okay, so A is at 1, 4, so over 1 up 4. So this is our A. Okay, so we have OA. And then our B is at 4, negative 3. Okay, so this is B. So, and then we want to look at finding our AB. So our AB, okay, is right here. So we know that if we add OA plus AB, we'll get OB. So just looking here, okay, if tail to tip, right, then this would equal OB. So I can rearrange this because I want to solve for what AB is. So AB therefore would be equal to OB minus OA. We know the values of OB and OA, so this works out perfectly. OB is just 4, negative 3, and OA is 1, 4. So we know how to do our addition and subtractions. So 4 minus 1, 3, and then negative 7, because negative 3 minus 4. So that is our AB, our vector AB. Now we want to find the magnitude. So the magnitude of AB is just those values that we found up here. Okay, so we can write this out if we'd like. It's just our minus x1 squared plus y2 minus y1 squared. So looking at our b value, okay, it's just going to be our 4 minus 1 squared plus our negative 3 minus 4 squared. 4 minus 1 is 3, 3 squared is 9. Negative 3 minus 4 is negative 7, negative 7 squared is 49. So therefore, we get the square root of 58. And if you'd like, because we're talking about magnitudes, you can go ahead and put this in decimal form, and you'll get that it's approximately equal to 7.6 units. So looking at our position vectors and magnitudes in R2, if A, which is x1, y1, and B, which is x2, y2, are 2 points, then the vector AB, which is equal to our x2 minus x1, y2 minus y1, is in related position vector OP. And AB is just equal to our square root of our x2 minus x1 squared plus our y2 minus y1 squared. So exactly what we did above, but now it just shows us our rule here. So in our next example, for the vectors x, which is equal to 2i minus 3j, and our vector y, which is equal to negative 4i minus 3j, we want to determine what the magnitude of x plus y is and the magnitude of x minus y. So our first step is to be able to find that is that we're going to go ahead and first find our x plus y. So to do that, we're just going to add our x and our y together by collecting our like terms since they are our unit vectors. So what I will have there is negative 2i because 2 minus 4 is negative 2 and minus 6j. So therefore x plus y, since we know our components, is just equal to negative 2, negative 6. So then to find our magnitude of x plus y, I'm just going to take the square root, or not the square root of negative 2 squared plus negative 6 squared, which would be equal to 4 plus 36, which is equal to the square root of 40, which in the exact form is 2 times the square root of 10. Now similarly, looking at our x minus y, so we're going to take our x, so 2i minus 3j, and minus our y, which is negative 4i minus 3j. And when we do that, collect our like terms, we're going to get 6i, and then the negative 3 plus 3j's are going to cancel out. So therefore, by components, I know that x minus y is just equal to 6, 0. And then to find our magnitude of x minus y, we just take the square root of 6 squared plus 0 squared, which would just be equal to the square root of 36, which is just equal to 6 units. So moving along here, in example 6, we have a, which is equal to negative 3, 7, b, which is equal to 5, 22, and c, which is equal to 8, 18, which are 3 points in R2. So what we want to do in part A is we want to calculate the value of the magnitude of AB plus the magnitude of BC plus the magnitude of CA, which is the perimeter of the triangle ABC. And then we want to calculate the value of the magnitude of AB plus BC. So let's go ahead and work on A here. So our first step is to find AB. So to find AB, remember we just take our x2 minus x1 and our y2 minus y1. So when we do that, so looking at B here, 5 minus negative 3, and then of 22 minus 7, and what we're left with is 8, 15. Then we can take the magnitude of AB. So the magnitude of AB is just going to be 8 squared plus 15 squared. When we calculate that, since 8 squared is 64, 15 squared is 225, we get 289, which is actually equal to 17. Now let's look at BC. So we know we need to take our second value of x, so our c value, so 8, minus our b value, our xb value, which is 5. Then our c, 18, minus 22. And we will get 3, negative 4. So now find the magnitude of BC. So we get 3 squared plus negative 4 squared. So 9 plus 16 square root of 25, which is just equal to 5. Now, last one here, we need to do CA. So CA, take your x value from A, so negative 3, minus the x value from C, 8, and then 7 minus 18, So we get negative 11, negative 11. So our CA, the magnitude, will be equal to the square root of negative 11 squared plus negative 11 squared, which will just be equal to the square root of 242, which when we calculate, it's approximately 15.56. So therefore, we can then add our magnitudes of AB plus BC plus CA, which is just going to be equal to, when we add up all the three of these, so our 17, 5, and 15.56, we're going to get 37.56. So that's A. Now B, we want to calculate the value of AB plus BC. So AB plus BC will just be equal to 8 plus 3 and 15 minus 4. Okay, those values come from our AB. So AB and our BC, the values we found in part A. So that will be equal to 11, 11. But also, if you remember, tail to tip needs to be added to tip to tail, or sorry, tail to tip to tail to tip, sorry. And when you have here, as we do here, we have our B's, so therefore this is actually just equal to our vector AC. And our vector AC is actually just equal to negative CA. Okay, and we know CA, which is negative 11, 11. So by that, we also therefore know that AC, the magnitude, is equal to CA. So therefore, the magnitude of AC is just going to be equal to the magnitude of CA, which is our 15.56. And that is example 6. And now for our last example of this part of our unit, so 6.6. Example 7, if our vector A is equal to 5, negative 6, and vector B is equal to negative 7, 3, and vector C is equal to 2, 8, we want to calculate the magnitude of A minus 3B minus a half C. First step, we need to first find A minus 3B minus a half C. So we're going to take our vectors here, so 5, negative 6, minus 3 times our B, so negative 7, 3, and then minus half of our vector C, so 2, 8. So this will just be equal, let's leave our 5, negative 6. We're first going to multiply in our scalars. So minus, just keep the minus out there right now, just multiply by positive 3. So negative 21 and 9, and then minus 1, 4. So now collect all of your x, right? So 5 plus 21 minus 1, and then negative 6 minus 9 minus 4. We're just going to get the point here, 25, negative 19. So now when we're finding the magnitude of A minus 3B minus a half C, this will just be equal to 25 squared plus negative 19 squared, which is equal to the square root of 986, so this will be approximately equal to 31.4 units. And that is the end of our lesson for today.